Okay, let's share screen. Which window? Okay, this. Fix my hair a little bit. Okay. Let me start my LinkedIn live as well. Okay. I don't like position of my camera on YouTube. Can I not move it? Edit. I don't think I can move camera on my YouTube thing. Hey. Okay. My LinkedIn live is open. Oh, let me just mute a little bit. Okay. Let's start. Let's continue. Where were we? Okay, let me see this function. Backward up. I'll go ahead and ask ChatGPT to explain this. Okay, I'm gonna start a new chat. I'm gonna do this. Explain this. While it's generating. Okay, I'll explain the code snippet, whatever. First, there is fake implementation for testing debugging. This thing is so crazy. I didn't even notice. Register fake here. Testing debugging. G is gradients. X tensor W, and this is the continuation of my previous stream. So X is the whatever activations or the numbers in the matrix, and W is weights. So those are gonna be converted. So I guess those will be FP8 converted to brainfloat 16 and then returned back. I just wonder what dot contiguous does. Let me ask. Why can't I edit this? Huh? Oh, I need to select whole line maybe. What does dot contiguous do? Method ensures the tensor is stored in. What do you mean ensures? Does it return true, false? This is the important. Oh my god. So does it return true or false or rearranges it? What does it do? Rearranges the tensor's memory layout to ensure it is stored in the contiguous block of memory. It does not return a Boolean value. Instead, it returns a new tensor with the same data but in a contiguous layout. So, does it create a completely new tensor and removes the old one? Does not modify the original tensor, but returns a new tensor with the same data in contiguous format. Contiguous memory layout, ensuring data is stored. I did not answer. Does it remove? Why is it not listening to my questions? Does not remove or modify the original tensor, but returns the tensor with new. data. Okay, let's accept this. Okay, next, I'm gonna just check my modifications of this file. Okay, that's it. Let's go back. Okay, what does this say now? Okay, actual backward pass implementation here. What is CTX? It looks like some kind of context, but I don't know what context. Okay, gradients out tensor, and then this saved context saved tensors. F, X, and W, and then scaling factors, and then gradient scaling. What is this grad S? I mean, it's probably scale. Grad W, grad X, ops, nano GPT, mm backwards. What? I guess this is defined somewhere. So we are registering fake function here. Let me just check. This is, yeah, defined here. backward. So it's gonna be ops, nano GPT, yeah, that's it. Okay. Explain context. Okay, I wanted to explain context and explain CTX and grad scale. Just that. Okay, let's see explanations for both of them. So gradient scale here. Why is it not working? What? Oh, it is working. Let's go. The context object is a context manager provided by PyTorch. So context object is a context manager provided by PyTorch's AutoGrad system. It's used to store information needed for the backward pass, manage the life cycle of tensors during the forward and backward passes, control how gradients are computed and stored. This is the whole thing about so many functions in the backward pass. Key methods: save for backward, saves tensors that will be needed during the backward pass. Scales a custom attribute to store the scaling factors. So these are scaling factors to convert from FPA to BF16 and stuff. Set materialize grads. What? Optimizes memory usage by not materializing. What does it mean to materialize gradients? What does that mean? What does materialize gradients mean? It's telling PyTorch AutoGrad system to avoid creating and storing gradient tensors unnecessarily. Here's what that means. Materialization in this context means creating actual tensor objects in memory. Allocating memory for gradient values, storing the gradient values in that memory. So just creating the tensor. So when gradients are not materialized, PyTorch only keeps track of the gradient computation graph, but not the gradient. It's just like how the gradient was computed, but not the gradient itself. Memory isn't allocated for the gradients. The gradients exist only as a computation recipe, not as factual values, so only the graph. Let's check here this example. Torch tensor 1 requires gradient true, okay. Backward materializes gradient tensor for X. So if you call backward pass here, print x gradient can and then you can access x dot gradient, can access the gradient as a tensor without materialization. Context set material as grads false. The gradient computation still happens, but no memory is allocated for the gradient tensor. The gradient exists only as a computation recipe. Can't directly access x dot grad. Okay. Okay. We can go back now. But did it explain grad s? Yeah. First, let's finish context. Okay. Optimizes memory usage by not materializing gradients unnecessarily. Here, context set materialize grads false. So just keep the graph, not the gradient value. So I think that's it. Okay, let's check gradient scale. Okay. Let's check this, then we will return to continue, like understand this better. This is called in this function backward, and we got it passed here, and we got it in the context scales. Okay. One of the three scaling factors used in FP8 matrix multiplication. Gradients are scaled for some reason. So XS scales factor for the input tensor. And then WS scales factor for the weight tensor. And then gradient scales factor for the gradients. That's kind of weird. These, okay, we know this. Scale process. The scaling process works like this. Forward pass, input tensor are divided by the respective scales. The operation is performed in FP8. The result is scaled back up. So the math move is performed in FP8. Yeah. Backward pass. Gradients are scaled by grad S. The backward operation is performed. Okay. The resulting gradients are properly scaled to maintain the correct magnitude. Why? I think like if you backprop once, you don't need those gradients anymore. This scaling mechanism is essential for maintaining numerical stability in low precision arithmetic, preventing overflow, underflowing. Okay, that's it. Okay, we know that. Why do you need gradients after you do backprop? I guess for gradient accumulation, and maybe parameter updates. The gradients tell you how to update the models. Wait, I said after, so I guess parameter update happens during the backpropagation, right? Oh my god. Uses, wait. Does parameter update happen during backpropagation? And let me select GPT-4o. Or why did you give all these examples? Okay, let's see. Backpropagation is the process of computing gradients of the loss function with respect to model parameters. Gradients of the loss function with respect. Okay, we want to minimize loss, so we compute gradients. It involves propagating the error backward through the network to calculate these gradients. During backpropagation, the model's parameters are not updated. Only gradients are computed. Okay. Okay. Parameter update. The actual update of the model's parameters happens after backprop. Okay, so that's why you need to store gradients and stuff. And optimizer uses gradients to update. Okay. Where were we? Let's go back. So we now understand gradient scale. So I'm guessing it will do gradient. So it will do gradient in FP, gradient calculation in FP8. Why this choice in particular? And updates in bigger precision. Why this choice in particular? Okay, FP8 is a lot faster. Memory. I know that's this, but why did it choose? Didn't answer my question. So I'm asking why FP8 for this and BF16 for that in particular. High throughput, matrix multiplication, especially in large language models, are. I don't think it's answering. It's not good. It's not good. Anyways, let's go to the next thing. We got this one, I think, covered. Yeah, we got that one. The context setup function extracts the scaling factors from the inputs. Scaling factors from, okay, what is this? Save. Okay, we can see here, save for backward pass. Yeah, that's okay. Into context, save scales. And okay, so are we extracting these things from context somewhere? Yeah, here. And where is this setup context called? Here. That's so weird. That's so weird. It's crazy. Op register autograph. That's so weird. Okay. I want to ask it. I want to add this to chat and say, why are these values saved into context and then immediately extracted? Do you even need to save them into memory? Okay, let's go. GPT-4o, don't disappoint me. Where is it? Why it's okay. Let me just check. Okay. Why is it so slow? Context is used to store information that is needed during the backward pass. This includes any intermediate results or constants that are computed during the forward pass and are required to compute gradients. Saving only the necessary tensors and data. Context helps manage memory usage efficiently. It ensures that only the required data is kept in memory, and other intermediate results can be discarded. Context provides a consistent interface to store and retrieve data between the forward and backward passes. This ensures that the backward pass has access to the exact data it needs to compute gradients correctly. Separation of concerns. The forward pass is responsible for computing the output and any necessary intermediate results. The backward pass is responsible for computing gradients. By saving data into context, the forward pass can pass necessary information to the backward pass without directly managing it. So the forward pass can pass necessary information to backward pass just by saving it to context. Some values might be computed during the forward pass, but are only needed during the backward pass. Saving them in context allows the backward pass to access, so some values might be computed during the forward pass but are only needed during the backward pass. Okay. Specific to this code, uh, in the provided code, the tensors xf8 and wf8, along with the scaling factors, are saved into context during the forward pass. These are then extracted during the backward pass to compute the gradients. Okay. Okay, so X and W FP8 matrices. These are the FP8 representations of the input and weights tensors. They are needed to compute the gradients with respect to the inputs and weights. Yeah, okay. Scaling factors. These are used to scale the gradients appropriately, ensuring numerical stability and correctness. Okay. Okay. Um, let's go back and continue. I guess we finished this, so I can summarize this backward. I can see Muon optimizer below. That's gonna be so tough, I think. But anyways, now wait a second. Ah, okay, okay. That's it. That's it. So backward pass. Where do we even call backward here? By the way, let me add all of this to a new chat. Oh my God, what's happening? Okay, so add to chat. Where is dot backward even called here? But I think we can go to Muon next. Muon is an optimizer that's gonna make, I think, like model train 2x faster. It's like a new optimizer. Anyways, let's just finish this. Loss dot backwards. Let me see where it is. If I click here, I don't see it. So let me loss dot backward. And there is two of them: training section and warm-up kernels. I guess we'll understand it eventually. It is what it is. Let's go to Muon. So this, let me just, so if we have Muon optimizer and a backward. Okay, Muon optimizer, that's gonna be a bit tough. I don't think I'm gonna get this, but let's just go through it. Newton-Schultz iteration to compute the zeroth power. Orthogonalization of G. What is G? We opt to use a quintic iteration whose coefficients are scaled to maximize the slope at 0. What did I read? What did I read? For the purpose of minimizing steps, it turns out to be empirically effective to keep increasing the slope at 0 even beyond the point where the iteration no longer converges. I don't know what I'm reading. Converges all the way to one everywhere on the interval. This iteration therefore does not produce u times v transpose, I guess. No, I don't know. No, it's not. It's u v what? But rather something like, oh my God, I don't know what I'm reading. I'll ask ChatGPT to explain this, I guess. Add to chat. Explain this Newton Schultz, whatever. Just explain it. Okay, purpose. Iteration is used to compute the zeroth power or orthogonalization of the matrix G. What? This is part of process to replace each 2D parameters update with the nearest orthogonal matrix. Quintic iteration. Okay, let me start asking. What do you mean 2D parameters update? What does that even mean? Parameters are just one number. Why is there two numbers in 2D now? Let me just start asking. In context of neural networks, parameters are often thought of as individual numbers, but they can also be orthogonalized into higher dimensional structures. What does it mean, orthogonalized? How can you orthogonalize a single scalar? Such as vectors, matrices, I guess they can be converted, I don't know, or even tensors, depending on the layer and its function. 2D parameters. In many neural network layers, especially those involving linear transformations, like fully connected layer or convolutions, parameters are organized into matrices. I know this. Why? Okay, oh my God. Okay. Fully connected layer, the weights connecting one layer to the next are typically represented as a 2D matrix, where one dimension corresponds to the input features and the other is output features. Each element in this matrix is a parameter, a weight, but collectively they form a 2D structure. That's what I meant, but it said here, it said something else. This is part of process to replace each 2D parameters update. So I guess update from each parameter from the 2D matrix. Oh my God, it's confusing. Okay, let's see what it says. Yeah, the term 2D refers to rows and columns. Yeah. Okay. What is this quintic iteration? The method uses a quintic iteration, which means it involves a polynomial of degree 5. The coefficients of this polynomial are chosen to maximize the slope at 0. Okay, let's start typing. Quintic iteration. Okay, what is this slope at 0? At 0 at which 0? At 0 or what? Okay, let me also read. Which helps in minimizing number of steps required for convergence. How does it help minimize number of steps required for convergence? The quintic iteration refers to an iterative method that uses a polynomial of degree 5 to approximate a desired result. Okay, uses polynomial of degree 5 to approximate a result, such as, so is it approximating the number or the function? I'm guessing the function, such as the inverse or orthogonalization of a matrix. So it's approximating function that's gonna orthogonalize or invert matrix. In this context, the slope at 0 is a concept related to the convergence properties of the iteration. In this context, slope at 0 is a concept related to convergence properties of the iteration. Convergence properties, convergence of what? So I'm guessing it's converging this polynomial towards the function that it's trying to approximate. Slope at 0. Understanding the slope at 0. Polynomial iteration. The iteration uses a quintic polynomial, which is a polynomial of degree 5. This polynomial is used to update the approximation of the matrix in each iteration. First of all, what? I don't get it. Wait. First of all, how can a polynomial approximate a matrix? So is it coefficients or what? In numerical methods, polynomials can be used to approximate functions or operations in matrices. This is done by applying the polynomial to the matrix, which involves using the matrix in place of the variable in the polynomial. Using matrix instead of the x in the polynomial. Okay. And then we're also gonna get some matrix in the end as a result, but there will be these changes. Okay, that's how, yeah, polynomials, they can approximate this function thing, whatever. A polynomial can be used to approximate a matrix function. For example, if you have a polynomial, whatever, you can apply to matrix A as follows. Yeah, okay, we understand that. Okay, where were we? Okay, let me go here. Quintic iteration. The method uses a quintic iteration, which means it involves a polynomial of degree 5. The coefficients of this polynomial are chosen to maximize the slope at 0. Is, again, I don't get this one, which helps it in minimizing the number of steps required for convergence. So I know that it's trying to converge matrix transformation function and polynomial transformation function of that matrix. So to make polynomial same. Okay. Okay. Matrix representation. Each element in the matrix is a parameter. Okay, I know this. Okay, slope at 0. Slope at 0 refers to the derivative of the polynomial at the point where the input is 0. Derivative at the coordinate center at 0. Why does it need to be? What does that have to do? In numerical methods, the slope at 0 can indicate how quickly the iteration will converge when starting from an initial guess close to 0. So you guess some number of, but which number? Is it number for like coefficients of the polynomial or what? You guess I guess a bunch of numbers. No. The number is the value, is the x value in the polynomial. Let's see. Slope at 0 refers to the derivative of the polynomial at the point where the input is 0. At the point where input is 0. So weird. The derivative of polynomial, okay, so polynomial is like also a function, and you take 0 and then calculate derivative at that place. Okay. In numerical methods, the slope at 0 can indicate how quickly the iteration will converge when starting from an initial guess close to 0. Why, by the way? But okay, a steeper slope at 0 means that the iteration can make larger progress in the initial steps, potentially leading to faster convergence. I guess because the step size is proportional to the slope, maybe. I don't know. I don't know. Convergence refers to how quickly the iterative method approaches the desired result, an orthogonal matrix. How quickly an iterative method, an orthogonal, what do you mean? How is orthogonal matrix desired result? I don't get it. By maximizing, yeah, wait. So we take our matrix, real matrix, we put it through some function, and this function is approximated by the polynomial. And the goal of this approximation is to convert our weights and activations matrix into orthogonal matrix. That's same, but like, I guess, the closest orthogonal matrix. So it's not going to be the same. It's going to be like changed, I think. I don't know. We'll see. By maximizing the slope at 0, the iteration can take larger steps initially, which can, I already read this. Application in Newton-Schultz. In the Newton-Schultz iteration, the coefficients of the quintic polynomial are chosen to maximize the slope at 0. To maximize the slope at 0 at this guy's iteration. This choice is empirical, meaning it is based on observed performance rather than theoretical guarantees. The goal is to make the iteration efficient by reducing number of steps required. Okay, so what I'm going to do now is I'm going to try to explain it, what I understand. So we have initial matrix, and we want to create a similar approximate matrix that is orthogonal. So we will pass it through some function, but it's easier to approximate that function with a 5-degree polynomial. So we will try to, what the hell are we gonna try to? I will not swear. So we will try to change numbers in the polynomial. But why do we need to first orthogonalize? I don't know how to spell this. What else? Pass it through some function, but it's why does higher slope mean faster convergence? Is it connected? What else do we need to ask? I guess why 5th degree polynomial? And explain, just explain. Orthogonalization is a process of transforming a matrix into an orthogonal matrix where the rows or columns are orthogonal unit vectors. So we have each row is orthogonal to other rows, I guess. Pretty sure that's how it works. This means, where was I? This means that the dot product of any two distinct rows or columns is 0. Okay. So they are orthogonal to each other. And the dot product of a row or column with itself is 1. Okay. Why? Benefits: numerical stability. Orthogonal matrices have desirable numerical properties, such as preserving the norm of vectors. Have desirable numerical, such as preserving the norm of vectors. What? Which can help maintain stability during computations. Preserving vectors between, so vectors are between 0 and 1, or what? I don't know. Optimization. In optimization, orthogonal updates can help in maintaining the directionality of updates, potentially leading to better convergence properties. Regularization. It can act as a form of regularization, preventing certain types of overfitting by maintaining the structure of the it needs to explain like why and how. Okay. Why does a higher slope mean faster convergence? Slope at 0 in the context of iterative methods, the slope of the function at 0 or near the initial guess can indicate how quickly the method will start. It's repeating my question. Faster initial progress. At higher slopes means that the initial steps of the iteration can make larger progress towards the solution. I guess step is proportional to slope. This is because the derivative slope indicates the rate of change of the function, and the steeper slope means a faster rate of change. It's not really coherent. Connection to convergence. I wonder if I change my model to, I'm going to change it to Gemini, this Pro. While the slope at 0 is not while the slope at 0 is not the only factor affecting convergence, it can significantly influence the speed of convergence, especially in the early stages of the iteration. Okay. Why a fifth-degree polynomial? Flexibility and accuracy. A quintic fifth-degree polynomial provides a balance between flexibility and computational efficiency. Okay, it's complex enough to approximate a wide range of functions accurately, but not complex that it becomes computationally expensive. Okay, let's read the explanation. Initial matrix. You start with a matrix that you want to orthogonalize. Function approximation. The process of orthogonalization can be complex. So you approximate it using a polynomial function. So if I approximate the process, so is the final matrix orthogonalized or approximately orthogonalized? You iteratively apply this polynomial function to refine the approximation of the orthogonal matrix. Wait. It doesn't make any sense. Okay, first of all, if I approximate orthogonalization is the final matrix, then approximately orthogonalized. Also, second question. So I am iteratively discovering both approximation polynomial values and applying it to the matrix, both iteratively. Let me ask that. Iteration, iterative, okay, I read that. Polynomial coefficients. The coefficients of the polynomial are chosen to maximize the slope at 0, which helps. Oh, I think this is yeah, this is not trained. This is just chosen, like these are the coefficients, I think, maybe. No, but this polynomial fifth, it has 5. Should have 5 of these, right? 0, 1, 2, 3, 4, 5. So 6 coefficients. I don't know. Okay, how are coefficients chosen? How are coefficients chosen? Okay, outcome. The result is an approximation of the original matrix that is, okay, I understand. The result is approximation of the original, so it's similar to the original but orthogonal. So it tries to keep it as similar as possible but orthogonal as well. So why does it say it approximates the process of orthogonalization? I guess even though you approximate it, it still like gives a orthogonalized matrix. Achieved efficiency through the iterative application of the polynomial. Let me ask these 3 questions. I'm going to use this better model maybe. Okay. Approximate, yes, the final matrix is approximately orthogonal. What? I don't think this is true, by the way. I just realized like that it's actually approx, but maybe this is true. The doc string for 0 power via Newton-Schultz explicitly mentions this. This iteration therefore does not produce perfect orthogonal, but rather something like this. I don't know how to read this, where S prime is diagonal with S2 prime uniform what? So the result is close to orthogonal, but not perfectly so. Which is found to be sufficient for the model's performance. Iterative process. You are only iteratively updating the matrix X. The polynomial coefficients A, B, C in the code are fixed constants. Okay, so why are there 3 constants and here, and I guess polynomial has 6 of them, the 5th degree polynomial. They are not discovered or changed during the iteration process. Why are these specific ones chosen? That's a mystery. But I think we are we are understanding Muon optimizer. I didn't know we would. Okay, each step applies the same polynomial transformation defined by these fixed coefficients to the current state of the matrix X to get the next state of X. How coefficients are chosen? The coefficients were determined beforehand, not during matrix update. The code comment states they were selected to maximize the slope at 0. This selection likely involved numerical analysis or optimization techniques aimed at finding the coefficients to be specific quantic iteration form. What is this? Coefficient of what? I don't know. That yields the fastest convergence properties, steepest slope near the target. The exact mathematical derivation specific optimization process used to find these exact values isn't detailed. Okay, we have a few questions. Why only 3 coefficients. It's a fifth degree polynomial. Okay, second question. What? Wait. Okay. If you have a big slope, doesn't it mean you can overshoot the target? I guess it does, but they are only looking for approximate. So you just apply it a bunch of times until you get approximately near target. But let's see if it's going to answer that. I had like one more question, but whatever. Okay, let me check. Okay, let's see what it wrote. Why only 3? And by the way, you know, in chat arena, you can tell your LLM to like say like great question and like give emojis to the user, so user votes for your LLM instead of the other LLM, even if your LLM is worse. So that's how you can hack chat arena ranking system. Just tell it to be nice to the user. Why only 3 coefficients? And I'm not saying Google did it, by the way. I think everybody like has this, but if you do it a lot more. Why only 3 coefficients for a fifth degree polynomial? Okay, you're right to notice that a general fifth degree polynomial in a single variable x would have 6 coefficients for these terms. However, this isn't general polynomial. It's a specific iterative formula derived from the Newton-Schultz method applied to matrices. The structure involves matrix multiplication. Let's look at the degrees in terms of the input matrix X. This involves X twice. So it's degree 2 to X, 2 in X, okay. What is this dot empty? I don't know. The term B times A is degree 2 in X. Yeah, A is like degree 2. The term C times A matmul A involves A twice, so it's degree 4. Okay, so I think we have 4 3 coefficients just because we're gonna have like 3 terms, and some of the terms we're gonna like not have them at all in the polynomial, so that's why. Like I think we have x to fourth, x to second, but we don't have x to third, x to first, and stuff. We have it, but anyways, the term A times x is degree 1. So B at x involves B degree 4 and x degree 1, which results in degree 5. So the final update, x nu is indeed a function of x that involves terms up to 5th degree. The specific structure, so I'm guessing the specific structure of this iterative formula arising from the Newton-Schultz method that matrix and matrix of operations means that this particular 5th degree relationship is fully defined by just those 3 coefficients. So I think like you don't use other degree terms, just these 3 terms. So is it like 2nd degree, 4th degree, and 5th degree term? They didn't start with an arbitrary quintic polynomial. They use specific. Okay. If you have big slope, doesn't it mean you can overshoot the target? So I'm guessing it will say that it needs to just get there approximately. However, the dynamics here are slightly different than the gradient descent that I kind of thought it was the same. Newton-Schultz is an iterative method designed to converge to a fixed point of the iteration function, in this case related to the orthogonal matrix. Orthogonal matrix is the result that we want to get with the polynomial, and polynomial is this iteration function. Normalization. The process starts by normalizing x. I guess it means putting all of the values between 0 and 1 to ensure its spectral norm is roughly within a region. Yeah, between 0 and 1. Okay. Convergence. While a steep slope accelerates the movement towards the fixed point, the iteration function itself is designed to pull the matrix closer to the target state with each step within its convergence basin. It's less about stepping past a target minimum and more about transforming the matrix into the what? Trade-off. The comment does hint at a related effect. It turns out to be empirically effective to keep increasing the slope at 0 even beyond the point where the iteration no longer converges all the way to 1 everywhere on the interval. I don't know what this says. This suggests that maximizing the slope for speed might slightly compromise perfect convergence, to the expected orthogonal matrix. Instead, it converges rapidly to the nearby state. Yes, that's what I said. Where S prime has diagonal values between, I don't know what this means. Yeah, prioritizing speed leads to a very close but not perfect orthogonal approximation. Yeah, that's it. Okay, okay, it was tough. Okay, so let me try to repeat everything. No. So we got some matrix that's weights and activations, like neuron values and weights. We want to orthogonalize this matrix to make each row or each column be orthogonal to each other, so their dot product is 0 for efficiency computation purposes. I still don't know how though. Okay, while I'm explaining, I'm going to ask, why do you need to make each row orthogonal? How does that improve computation? Anyways, the way we orthogonalize is we have initial matrix and we want to pass through some function, and that function is gonna move it a little bit more towards it being orthogonal matrix, but just a little bit more. And next time we pass this new matrix through the function again, it's gonna move a bit more. And we do it until we get as close as possible to the orthogonal matrix. I guess we are getting to the orthogonal matrix that's most similar to the starting matrix that we have. And this function, convergence function, is just a 5th degree polynomial that's approximating convergence function. So the resulting orthogonal matrix will also be approximation. And we only have 3 coefficients because I guess we are using 3 terms in the 5th degree polynomial, like 2nd, 4th, and 5th degree terms. And these coefficients are just they are selected by some like reasons. Maybe they found them to make slope at 0 of the polynomial as large as possible. So it's gonna make as big steps as possible when moving towards this matrix. But I don't know, like 100%. Like I can't imagine it 100%. Maybe I can ask. So what are these steps that are being made? So is the derivative being subtracted from each value in the matrix? And I guess let's wait for this just a few seconds. Okay. You've got the right idea about subtracting the derivative or gradient. Let's look at the specific step made in the Muon optimizer for a single parameter p, but I don't think I'm asking about Muon optimizer, because I think this is happening before the optimization. This is just converting the matrices to orthogonal. I don't know, let's see. Calculate momentum, adjusted gradient. I see Mythos, you just sent some messages. I don't know when you send them. I was reading my stuff. Can you give a brief explanation of what you're working on? No problem, I lost the interest. Check out my latest video on my channel. It's gonna be like how to train LLMs quickly from scratch. Something like that. And I'm improving that architecture. Okay. Gradient, calculate momentum, adjusted gradient. First, the raw gradient, P grad. What is this P now? Is combined with the previous momentum buffer. What? Momentum buffer. So I guess we have some momentum. Buffer is the place where that momentum value is stored in memory, I guess. To get an updated gradient direction. Wait. Okay, so we have momentum. And then we combine somehow the raw gradient with the previous momentum. So is it going to change the momentum? I don't know. Is momentum? Yeah, momentum is probably a single. Yeah, gradient shows the direction, and momentum is like a scalar value, I'm guessing, that says that's going to amplify the gradient or reduce the gradient length, because optimizer will make an update that's proportional to the length of the gradient or the derivative at that particular place. So we have momentum to indicate, to make sure like everything is moving, so there is no like sudden changes. So if the gradient is suddenly going to different direction and we have momentum in this direction, then the momentum will slow down the gradient. It will prevent it from going so hard into this other direction. So so it kind of tries to keep it constant, I guess. Let's see. First, the raw gradient P. Still don't know what this is, by the way. Okay. This is standard stochastic gradient set momentum. Okay. First, the raw gradient, P gradient, I guess this is our gradient of our stuff, is combined with the previous momentum buffer to get an updated gradient direction. This is standard stochastic gradient descent momentum. Yeah. Buff is the momentum buffer. Okay. Momentum buffer is, I guess, memory or something. What is this? Update momentum buffer. What is this? Do I actually have this in my code? Yeah, I do. And what does it do? I don't know. I guess we'll look into this later when we get to this part, which is very close. Orthogonal is the gradient G. This is the unique Muon step. The momentum adjusted gradient G, which is a matrix for these 2D parameters, is passed through the Newton-Schultz iteration to make it approximately orthogonal. The momentum adjusted gradient G, which is a matrix for these 2D parameters. What? The momentum adjusted gradient G, okay, which is a matrix for these two parameters, the 2D parameters. Okay, we have a matrix. Each of the values in the matrix is a single derivative for each parameter. How that parameter changes the loss function, I guess, is passed to the Newton-Schultz iteration to make it approximately orthogonal. 0 power via Newton-Schultz. So that's this function. So we get G is the matrix that we want to orthogonalize, and steps is the number of steps. But I didn't know we are predetermining number of steps. I thought it's gonna do steps until it converges. So I don't know why we have predetermined number of steps. What is this group? I don't know. I guess, why do we have predetermined number of steps? I thought it will do steps until it converges. Ugh. Okay, now G is still a matrix representing the direction of the update, but it has been transformed. Let me check. To be approximately orthogonal. But why? Why? Okay. Why do we need, like, explain mathematically what happens with the optimizer updates if the matrix is orthogonal versus not orthogonal. Okay. Apply the update to parameter P. This is where subtraction happens. The parameter P is updated using the add method, but notice the alpha scaling factor. Parameter P add G view as P. Okay, yeah, okay, that's okay. Just gonna make sure it's same shape, but that's okay. Alpha group learn what? Subtracting the learning rate. Okay, but just what is this group? But okay, so subtracting the learning rate times maximum of 1 and parameter size to second power. What is this? Okay, wait. Performs the operation. So P add performs alpha scale. This is some kind of scale. Here, value is the orthogonalized gradient G. Scale, the alpha, includes the negative learning rate. So the update is effectively new parameter value is old plus negative learning rate for some reason. Times shape factor. I don't know what I'm reading. I don't know. Or times orthogonal P new. I don't know what. Okay, in summary, the optimizer takes a step by effectively subtracting a scale version of the process gradient from the current parameter values. The key differences from the standard gradient descent are: gradient g is first adjusted by momentum. Momentum adjusted g is then transformed via orthogonalization using Newton-Schultz. The final subtraction uses this orthogonalization. What? The gradient g is first adjusted by momentum. Okay. This momentum adjusted g is then transformed via orthogonalization using Newton-Schultz. We got us nearby orthogonal, I don't know why yet, we'll read. The final subtraction uses this orthogonalized g and includes an additional scaling factor based on the parametric shape. What? The final subtraction uses this orthogonalized g and includes an additional scaling factor based on the parameters matrix shape. What? It's random. Why? Okay, I mean, we have to sometimes skip something. Why do we have predetermined number of steps? I thought it will do steps until it converges. You're right, many iterative algorithms do run until they meet a specific convergence criterion. The change between iterations is below a threshold. However, using a fixed number of steps for the Newton-Schultz iteration within the Muon optimizer is a deliberate design choice based on several blah, blah, blah. Computational predictability and efficiency. Okay. Sufficient approximation. Okay. It's gonna converge sufficiently. Optimization and compilation. Fixed loop counts are generally easier to compile for compilers like Torch compile to optimize into efficient GPU kernels compared to loops. Okay. The primary convergence we care about is the convergence of the model parameters over the entire training process, thousands of training steps, driven by the sequence of optimizer updates. The convergence within this convergence is secondary. Okay, so my question would be, there is a matrix and you are trying to make more orthogonal matrix, but not perfectly. Why? Okay, but maybe that question is answered here as well. Explain mathematically what happens with the optimizer updates if the matrix is orthogonal versus not. Okay. Mathematical effect of G. A general matrix G represents an arbitrary linear transformation. Okay. When applied, even just in subtraction, it can rotate, scale, shear, rotate. So we have these two vectors. You multiply them with a matrix, it can rotate the two vectors or one vector, or it can reflect. Okay, that's what matrix does. Multiplication with a matrix. It's called linear transformation. Impact. The update step is influenced by both the direction and the magnitude inherent in G. The update step is influenced by both the direction and magnitude inherent in G. The update step is influenced by both direction and magnitude. So it's going to change direction and can increase magnitude of the vector. If G has very large entries or a large normalization, how it does this influence, I have no idea. The update step can be very large, potentially leading to instability Exploding parameters loss. If G has very small entries, the update might be too small. Vanishing gradients updates. The update reflects the raw geometry of the loss landscape grade. What? The update reflects the raw geometry of the loss landscape gradient. The update reflects the raw geometry of the loss landscape gradient at that points. What? I thought the update reflects the direction in which to move or moving, not the geometry, landscape geometry. I don't know. Maybe it's the same thing. Muon update, approximately orthogonal gradient O. The update rule is new weight is old weight minus. This is going to be scalar value for the, I don't know what this is. Mathematical effect of O, orthogonal gradient. Orthogonal gradient, yes, so orthogonal, so each row or each column is orthogonal to each other, every other column or every other row. An ideal orthogonal matrix O represents a transformation that preserves distances and angles. Yeah, wait. So this is ideal, but yeah, matrix can also do this, I think. Not just rotate, it can both like same, but it can also rotate them independently, the vectors, the linear transformation. So that's what matrix can do. I guess what they want to do is rotate vectors without together, with keeping angles between them. So it's a bit confusing. So I guess we can look at optimizer updates as linear transformation. I'm still trying to like imagine how, but because optimizer takes a matrix, multiplies weights. So that's whenever you multiply something with a matrix, you're doing linear transformation of those vectors or matrices or dimensions or whatever. So I guess it's trying to keep angles for some reason. I don't know why. Rotation, change of orientation. Reflection, flip. No scaling, shearing. Okay, so orthogonal matrix can rotate and reflect, but not scale. An ideal orthogonal matrix does not stretch or shear the space. So I guess shearing would be like this. If this is vector from, I don't know. Let me check, okay. Approximation. Since the Newton-Schultz method used here produces an approximately orthogonal matrix O, its singular values are close to 1, mentioned as roughly 0.5 to 1.5. Why? In the comments, why? Okay, why is it 0.5 to 1.5? Let it answer here, but I'm gonna continue reading. It's gonna be which one? This one. I stop scrolling my screen here. It primarily performs rotation reflection with only mild controlled scaling because it's approximate. So that's why there is mild scaling. The direction of the update is still derived from the original gradient, yes. But it's projected onto the space of nearby orthogonal matrices, okay? Magnitude of the update is primarily controlled by the learning rate, okay? The intrinsic magnitude or scaling effect of the original gradient G is largely normalized away by the orthogonalization. Normalized. Wait. The intrinsic magnitude or scaling effect of the original gradient G is largely normalized away by the orthogonalization. Why do you want it to be normalized away? Why do I thought like the steeper the slope, the more you want to update, the bigger step you want to make. So now it's saying like you want to reduce the step on a steeper slope. I don't know. The resulting matrix O has a controlled norm close to what an ideal orthogonal matrix will have. The resulting, what does it say? The resulting matrix O has a controlled normalization close to what an ideal, what the resulting matrix O, what is this O? Where? What? It's approximate orthogonal matrix. Okay. The resulting matrix O has a controlled norm close to what an ideal orthogonal matrix would have. Okay. Okay. This leads to more controlled, stable updates, but maybe slower updates. Didn't you think about that? I think it just leads to smaller updates, so slower updates, because it's stretched down. The step size is governed more directly by the learning rate rather than potentially erratic magnitudes of the raw gradient. True. So now we are normalizing each gradient, and now we can control it better just with the learning rate. So now it's not like random magnitudes. But I thought like the higher the magnitude of the gradient derivative means like higher slope, which means you want to take a bigger step on that slope. So I don't know. We'll figure it out eventually. Everything will make sense eventually. It avoids drastic uncontrolled scaling of the parameter space during the update. Drastic uncontrolled. I think learning rate already took care of the drastic uncontrolled scaling of the parameter space. So it means walking, how do you say? I don't know. Not transferring, transitioning, what, I don't know. Okay, let's continue. Let's skip this. I'm done with this. Okay, there is a matrix, and you are trying to make more orthogonal matrix, but not perfectly well. I think we already understand this. Finding, okay, that's difficult. Finding exact is difficult. You need to approximate. Okay, well, let's skip this. Y is between 0, 5, and 5. So the range 0, 5 to 1.5 for the diagonal elements of S prime, which corresponds to the singular values of the resulting matrix, isn't a strict mathematical derivation or requirement. Instead, it's an empirical observation described in the code's comments about the outcome. Instead, it's an empirical observation described in the code's comments about the outcome of using that specific quintic Newton-Schultz. I know, bro. I'm asking, why did they choose these numbers? Target value. The goal of orthogonalization is to produce matrix whose singular values are all of what? So what are singular values in a matrix? Draw and explain why they need to be 1. What are the benefits? Okay. Prioritizing speed over perfection, we know that. Fixed number of steps. Okay, that's all good. That's all good. Empirical range. The range uniform between this is author's way of describing the observed spread of final singular values around the target value of 1 when using this specific fast approximate. Okay, let's read this. What are singular values? Imagine a matrix A as a function that transforms vectors. If you take all the vectors that form a unit sphere, a sphere with radius 1, in the inputs. Okay, so this is what it says. We have 0 center, all vectors, same length, and they are forming a sphere when you extrapolate. And we have some matrix. Matrix is going to rotate those vectors. Let's see what's going to happen. In the input space, and apply the matrix A to them, to that sphere. The resulting shape in the output space will be an ellipsoid. Yeah. Or a lower dimensional equivalent if the matrix isn't full rank. Yeah, well, I mean, we have some vectors, matrix will rotate, stretch, so you will have a sphere, you can get like this. But can't you, like, is it gonna not, some of them are not gonna scale the size? I think not. I don't know why it didn't scale size for some vectors. Yeah, it did actually, because to get a sphere, some vectors from 0 need to be longer, so it scaled the size. But why did it scale size so uniformly so it creates a sphere or ellipsoid? Let's see. Singular values are the lengths of the semi-axis of this resulting ellipsoid. Singular values are the lengths of the semi-axis. What are semi-axes of this resulting ellipsoid? They represent the stretching and scaling factors that the matrix applies along. They represent the stretching or scaling factors. Stretching, scaling, yeah, it's the same thing. That the matrix applies along specific orthogonal directions in the input space, called the right singular vectors. To produce orthogonal directions in the output space, called the left singular. Wait, orthogonal direction. What am I reading? They represent the stretching or scaling factors that the matrix applies along specific orthogonal directions in the input space, called the right singular vectors. To produce orthogonal directions in the output space, called the left singular vectors. I don't know what I'm reading. Oh my God. They are always non-negative. They are typically listed in descending order. What is, I don't know what I'm reading. This is formally captured. Let's just skip. I don't know. This is formally captured by the singular value decomposition. Okay, I know what this is. I don't know. Any matrix A can be decomposed as what? U is an orthogonal matrix whose columns are the left singular vectors, directions of the ellipsoid's axis in the output space. V is an orthogonal matrix whose columns are the right singular vectors, directions in the input space that get mapped to the ellipsoid. Oh my God. Okay, but I understand. So we transform the sphere to ellipsoid with a matrix. So U is the sphere. U is the sphere, like I don't know, something in the sphere, and V is something in the ellipsoid. That's what I understand. Sigma is a diagonal matrix containing the singular values. What is this? What is this sign? I forgot. Omega on its diagonal. Okay, let's see some visualization. Imagine a matrix A acting on vectors in a 2D plane. Okay, that's it. Matrix can transform vectors, move them around, scale them, stretch them, change angle between. Okay. Input space. Start with a unit circle, a 2D shape. The vectors 1, 2, 1, 0, and 0, 1 are examples of orthogonal unit vectors. What am I reading? Vectors 1, 0, and 0, 1 are examples of orthogonal unit vectors in this circle. Okay, so 1, 0 is this vector on the x-axis, and 0, 1 is this y-axis vector. Oh my god, oh my god, oh my god, oh my god. Okay, we got this. I guess 0 is here in between, so we got, this is 1, 0. This should be 0, 1. I guess. What is this? 2x, 1x? I don't know what this is. Transformation by A, apply matrix A. So we apply A times array of vectors. So each of these asterisks is one vector, I think. And they give unit circle, I guess. Output space. The unit circle is transformed into an ellipse, or the original orthogonal vectors 1, 0, and 0, 1 are mapped to new vectors that point along the axis of the ellipse. Okay. After potentially being rotated by u. Okay. X-axis of the circle, y-axis of circle. First of all, this y-axis vector can stretch because we are multiplying this with the matrix, so we can stretch. It can also rotate like this, but it will not change angle because the matrix we are multiplying it with is orthogonal. And that's all I can explain. I don't know why it's, I don't know. That's it. The lengths of the the lengths of the semi-axis of this ellipse, the lengths of the what is semi-axis? What is this? Is this like y-axis? I don't know. Oh, maybe it's half of the axis. Half of the axis. The lengths of the semi-axis of this ellipse are the singular values omega 1. Oh, is it sigma? It is sigma. It's not omega, it's sigma. Wait, let me just check quickly. Sigma. Small. Sigma. Yeah, this is sigma. Okay. Why do singular values need to be 1 for orthogonal matrices? I still don't know what a singular value decomposition. So I guess singular value is the value on x-axis, the vector on x-axis, so this vector, and vector on y-axis, this vector. So I'm guessing that's what singular values are. So why do singular values need to be 1 for orthogonal matrices? An orthogonal matrix represents a rigid transformation, only rotation and/or reflection. It preserves distances and angles. As we said, just gonna rotate or reflect, but not change this stuff, or like shear. Okay, if you apply a rigid transformation, like rotation, to a unit sphere, what shape do you... If you apply a rigid transformation, like rotation, to a unit sphere, so what we can do is rotate the sphere and reflect the sphere, so we should get the sphere. You still get the exact same unit sphere. Let's go. Just possibly oriented differently, but since it's a sphere, you don't even see that it's a sphere, bro. Can't see the orientation difference. Yeah, it's oriented differently. Yeah, that's true. If the transform shape is still a unit sphere, what are the lengths of its semi-axis? They are all 1. I guess because they were 1 in the first place. Therefore, for a matrix to be orthogonal, all of its singular values must be exactly 1. For a matrix to be orthogonal, I still don't know what a singular value is, bro. Matrix, I'll search it. Singular value. Singular value seems to be, I have no idea. To this day, I don't know what a singular value is. Draw it. I don't know what a singular value is. Let's wait for this a little bit. Okay. Let's try a different visual approach using text art. The guy is struggling to explain this to me. The starting point, a unit circle. Think of all the possible directions you can point from the center with the length of exactly 1. This forms a perfect circle, yeah. You can represent directions using vectors, yeah. 2 important orthogonal perpendicular directions are along the axis. Yeah, 2 important directions are the x-axis and y-axis. They are perpendicular, yeah. So are these singular values? Are these vectors? The circle represents all vectors v with length v is equal to 1. So length magnitude of v is equal to 1. This is funny. So is this absolute value of magnitude of v? The transformation apply matrix A. Now take 2x2 matrix A. With this matrix acts like a function that takes any vector v from the circle and transforms it into a new vector A times v. Let's apply A to single vector on the original circle. Okay. The result, an ellipse. When you apply a typical matrix A to all the points on a unit circle, the circle gets stretched, squashed, and possibly rotated. The resulting shape is an ellipse. If it's 2 times 2, like I would say it would still be the circle, but I don't know what I'm saying. So identify the singular values, sigma 1 and sigma 2. Now look closely at the resulting ellipse. Where? It has longest diameter, the major axis, and shortest diameter, the minor axis, which is perpendicular to the major axis. Okay. The singular values are the lengths of the semi-axis half the diameters. Okay. Okay, so this is, so you take this short diameter of the ellipse, half of it is the singular value, and half of this long diameter is a singular value. So these two vectors, so this is one vector going from 0 to this point, and from 0 to the shortest, closest point here. Those are singular values. Okay, that's why it's called singular value decomposition. So if you rotate, yeah, anyways, I don't want to confuse you. Okay. Okay, I think we get it. We get this now. Oh my god, we get this now. Okay, let me chill a little bit. Let me chill for a minute. Let me just check something. Oh my god, it's 1 hour 40 minutes the stream. Okay. Okay. Oh my god. Okay, let's continue. I don't know where I left off, what I need to do. I guess right now I'll just tell it to explain Muon optimizer. Add to chat. Explain Muon. Okay, let's see. I guess now we're able to understand it a little bit easier. I don't know. Okay. Let's break down the Muon optimizer based on the code provided. Momentum orthogonalized by Newton-Schulz. That's the name where name comes from. We have momentum orthogonalization. Okay. Core idea. Muon combines two concepts. Standard stochastic gradient descent with momentum. So that's the first concept. It first calculates the parameter update direction. Parameter, so the gradient. Parameter update the direction, so the classic stochastic gradient descent with momentum. So it's gonna keep the track of where each gradient in each step is like pointing towards, and the length and the size of the gradient. And optionally Nesterov momentum. I don't know what Nesterov. Let's not look into this now. This gives you a preliminary update matrix G. Okay. Orthogonalization post-processing. Instead of directly applying this raw update G, Muon modifies it. It finds the nearest approximately orthogonal matrix, okay, to G, and uses that orthogonal matrix as the final update direction. Okay. Why orthogonalize the update? I can remember. I can't remember. As we discussed, orthogonal transformations primarily involve rotation, reflection, and preserve lengths, or nearly preserve them in this approximate case. Yeah. By making the update matrix orthogonal, the optimizer ensures the update step doesn't excessively wait, I need to read this again. By making the update matrix orthogonal, the optimizer ensures the update step doesn't excessively stretch or squash the parameter space in arbitrary directions dictated by the raw gradient magnitude. Okay, so I guess this is the logic. Gradient magnitude is showing you where towards what to update gradients, but that may not be the best for some reason, and somehow we will improve it. I don't know why and how. Let's see. This aims to stabilize training dynamics, preventing updates from becoming too large or too small. I guess the same like with you don't want to make too big steps and overshoot local minimum or global minimum, or too small updates that you don't move at all. Yeah, I think that's it. Because if the loss landscape is very how do you say, not steep, yeah, it's very not steep, then we are making grade steps proportional to derivative, but the derivative is not steep, not big. So it's small derivative, I'm guessing, like near zero. So you're gonna traverse that part of landscape very slowly because the derivative is very small because it's not steep. So you wanna use these muon orthogonalization to, I don't know what to do with it. It somehow, I guess, makes it bigger steps. I don't know how. This aims to stabilize training dynamics, preventing updates from becoming too large or too small, and making the step size primarily controlled by the learning rate. Okay. How is orthogonalization done efficiently? Calculating the exact nearest orthogonal matrix often requires singular value decomposition, which is computationally expensive. That's why we approximate it. We use zeros, so we use the fifth fifth degree polynomial. We pass our matrix to that polynomial one time. That polynomial is made, so it's gonna transform our matrix into a little bit more orthogonal matrix where dot product between rows or columns is zero. Yeah. And we pass this matrix multiple times through this polynomial. So this polynomial is just a approximate function approximating this function that's expensive computationally. So this singular value decomposition matrix linear transformation thing. So this polynomial, we pass it multiple iterate. So this function implements the Newton-Schultz iteration, a numerical method for a fixed number of steps. Yeah, because we can easily use torch compile when we have a fixed number of steps in a for loop, as opposed to letting it converge. But then we don't know like the number of steps it will use to converge. It will be different every time. So we want a fixed, even if it's going to be a bit less of convergence to improve computation speed. This iteration efficiently approximates the orthogonalization using matrix multiplication. Yeah. This iteration efficiently approximates the orthogonalization using matrix multiplications, which are fast on GPU. But if you used singular value decomposition, it's also a matrix multiplication, I think. Let's ignore this and continue. Okay. Especially in bflow 16. Why especially here? I don't know. Maybe we'll figure out next time. It gets close enough to orthogonal for the desired stability benefits without the high cost of singular value decomposition. Okay. The step method explained. Get gradient. It retrieves the gradient p parameter dot gradient for a parameter p. Okay. Calculate momentum update. It computes the standard momentum adjusted gradient using the stored momentum buffer. So we have momentum buffer that's going to be a scalar value, I think. What is this LARP? Linear or interpolation or something? I don't know. G1 minus, so this is just a calculation formula based on momentum buffer. And then orthogonalize. Okay, it applies Newton-Schultz iteration to G. Yeah. The number of steps. We have this this is a hyperparameter, I'm guessing, or something. Apply update. It adds this orthogonalized G to the parameter P scaled by the negative learning rate and the factor related to the matrix shape. Why? Why scaled by negative learning rate? Distributed training. The multi-GPU implementation uses this still all gather. What is this, bro? What is this? Multi-GPU implementation uses distill all gather into tensor to efficiently collect the locally computed orthogonalized updates G. What? From each GPU onto all other GPUs, allowing all ranks to update the parameters consistently. It uses asynchronous operation to overlap communication and computation. What did I read? Allowing all ranks to update the parameters consistently. It uses asynchronous operations to overlap communication and computation. Limitations. The docstring explicitly warns. The docstring explicitly warns that Muon is designed for 2D parameters like weights matrices in linear layers. It's not recommended for embedding layers, final classification output head, scalar parameters. These other should be used with Adam W. Okay, I want this to explain this number 5 more, and once it explains these two questions, I think we're done with Muon. Even though I'm not able to re-implement it, where I've been looking at it for 2 hours today, it's enough for Muon. Maybe we can go into something below that's gonna be easier. Now, why is this generating for so long? Let me take a look. My LinkedIn stream is so behind. It's like so behind. I don't know why. Maybe it's not. Maybe it's just showing to me. Okay, why is this not working? I will use ChatGPT. Actually, I might look to restart. Let me look to restart this. What is this? What is this? How do I close? What? Close window. Okay, and let me open cursor. Okay. So now in my streamings, okay, this is streaming properly. LinkedIn is streaming, okay. Let me check YouTube stream. Okay, there is nothing in here. Let me select my window again. Share, okay, and let me send this. I hope this will work this time. Sometimes, yeah, I need to restart my cursor so it removes this bug where this chat doesn't work. So I guess my YouTube stream works and my I don't know if my LinkedIn works, by the way, but it is what it is. It is what it is. Let's go. Okay, why scaled by negative learning rate? This is fundamental to how gradient-based optimization works. Yeah, this is easy. So gradients show where the loss function is ascending, so you want to go in the opposite direction. So that's why it's negative. And learning rate, just to make the update less, not too big. Gradients are big. Okay, distributed training explanation. This is the last thing for Muon. This part describes how Muon handles training across multiple GPUs efficiently. The challenge: when training on multiple GPUs, let's say n GPUs, each GPU typically works on a different slice of the data, a mini batch. Each GPU calculates gradients based only on its local data slice. However, to update the model correctly, you need an update step that reflects the gradients from the entire batch across all GPUs, okay? Also, the model parameters on all GPUs must remain identical after each update step. Yeah. So you need to update model parameters. I mean, after you update model parameters, you need to update them on each GPU. I don't know. Muon strategy. Local computation. Each GPU identified by its rank from 0 to n minus 1. Yeah. Computes its local momentum adjusted gradient G and then orthogonalizes it using 0 power via Newton-Schultz. Okay, we were talking about this for 2 hours now, so let's go on. This G only reflects the data seen by that specific GPU, okay? Just the mini batch on that GPU. This still all gather info tensor update buffer async. What is this? This is the crucial communication step. All gather. Okay. Each GPU sends its locally computed tensor, G, to every other GPU, including itself, into tensor. The receiving GPU collects all these n tensors, one from each rank or each GPU, and stores them contiguously in a pre-allocated buffer. Update buffer views is likely a list of views into this buffer. What do you mean into this? What? Making it easy to access the G contributed by each specific rank. Okay, so I guess like every GPU sends its computed gradients to every other GPU. Result: after this operation completes, the update buffer on every single GPU contains the full set of orthogonalized updates G computed by all the GPUs. Okay, I don't know why, but it is what it is. Parameter update. Update previous function. Now that every GPU possesses the complete set of updates from all ranks within update buffer views, each GPU can independently calculate the final update for the parameters. Since why does each GPU need to calculate it independently? Can't like one GPU calculate it and then send it to every other GPU? Maybe it doesn't matter. Maybe there is no optimization to be made here. It doesn't matter. Maybe since they all have the same information and use the same update rule, parameter world.add, I guess this is just adding. So adding the gradient, transformed, orthogonalized, whatever, to the weight. They will arrive at the same exact final parameter values, keeping the model synchronized across all GPUs. Now, what if it doesn't? Anyways, asynchronous operation. This is an optimization. It tells the system to start the all gather communication, but allows the GPU to continue executing subsequent code without waiting for the communication to finish. The actual waiting happens later using handle wait here. It's actually quite far. Okay, handle wait. This allows computation, preparing the next step and communication, sending, receiving G to overlap. Yeah. Hiding the communication latency and speeding up training. Handle weight, but how much does it weigh? I don't know. In essence, this all gathering tensor is a mechanism used to efficiently share the locally computed orthogonalized updates amongst all GPUs. Each GPU sends to every other GPU. It's part of the gradients it computed for the mini batch. It's part of the batch. Ensuring that every GPU has the unnecessary information to perform the correct synchronized parameter update for distributed training. I think that's gonna be it for this Muon. I'm done with it, bro. I'm done with it. I'm done with it. Okay. I don't know. What is this? Maybe I'm gonna end the stream here and come back like a bit later in an hour. But there are people watching right now. So I don't know. Yeah, okay. Let me end it now. I'm gonna come back in an hour. Okay. Goodbye, guys. Thank you for watching. Goodbye.